All right, this is on logarithmic functions. How many times would you have to double $1 before you get to 8? You can use an exponential equation to model this situation. So it would look like 1 times 2 to the x, which equals 8. You may solve this equation by using mental math. So 2 to the third power is 8. So you would have to double dollar 3 times to get to 8. So a little harder now. How many times would you have to double $1 before you get to $512? You could use an exponential equation again to model this by using an inverse operation, which undoes raising a base to an exponent. This operation is called finding the logarithm. A logarithm is an exponent to which is a specified base is raised to. So here's what it looks like. So we will be converting between these two forms quite a bit. And you have to just memorize the order. So the left-hand side of the equation set is an exponential equation. So it has the base raised to the exponent and then what it equals. Now notice if we go to the right-hand side equation, the logarithm equation, we call that log base b of a equals x. Notice where the base, the exponent, and the value change spots. And again, you have to memorize these two equations. So example 1. Convert from an exponential, so what we have here on the left, to the right. So an exponential equation, 2 to the 6th power equals 64, and we want to change that to a logarithm. So how that'll look is we say log base 2, so it's a little subscript, and then what it equals goes in next of 64, and then the exponent goes off to the right. Let's do the next one. 4 to the first power equals 4, so to write that as a logarithm, it's log base 4 of 4, and again that exponent goes off to the right. Third example, 5 to the 0 power, anything raised to the 0 power is 1. How do we write that as a logarithm? Log base 5 of 1 equals that exponent number. The next one, 5 to the negative 2 power equals 0.04. So it's log base 5 of 0.04 equals -2. Last one, log base 3 of 81 equals x. Example 2 now is we are going to give you a logarithm equation and we want you to convert it to an exponential. So again, we're with an equation onto the right and we want to make it look like what's on the left as an exponential. So our base is our subscript 10. What's off to the right of the equation is your exponent, so that's 2. And then the of is 100. So check it. 10 times 10, yes, equals 100. Next one, log base 7 of 49 equals 2. So the base is 7, the exponent is 2, equals 49. Check it. 7 squared, 7 times 7 is 49. All right, log base 8 of 0.125 equals -1. So 8 is the base, exponent of -1 equals 0.125. Next one, log base 5 of 5 equals 1. So 5 to the first power equals 5. Last one, log base 12 of 1 equals 0. So 12 to the 0 power equals 1. A logarithm is an exponent, so the rules for exponents also apply to logarithms. You may have noticed that the following properties in the last example. So here are two special properties. The logarithm of base b. So as a logarithm, it's log base b of b equals 1. As an exponent, b to the first power equals b. So then there's an example of both of those to the right. So if we had a base of 10 raised to the first power, it does in fact equal 10. The second property is a logarithm of 1. Log base b of 1 equals 0. In exponential form, b to the 0 power, anything to the 0 power is 1. And then here are two examples off to the right. The other thing is what we call a common log. A logarithm with base 10 is called the common log. If no base is written for a logarithm, the base is assumed to be common log. So you'll see it converted where they just drop the 10. That is assumed that it is base 10. If the logarithm is using base 10, it is customary to just drop the number 10 because it is understood. So these two things equal each other. That's called the common log. All right, a property. One-to-one property of exponents. When you have two exponential equations and they equal each other and their bases are both the same, so then our powers, our exponents, will equal each other. So here's our bases. They're both base a. And that means then the exponents will equal each other. So we're going to go ahead and move on to example 3, where it says solve for x using that one-to-one property. So right now example A says 4 to the 2x equals 4 to the second. And we want to find out what x equals in that equation. So we can use our one-to-one property. Our bases are both 4. So that means our exponents must equal each other. So I'm just going to focus on 2x equals 2 because our bases are both 4. And now we just solve it like we do a linear equation. We solve by undoing. We use our inverse operations. So we're going to divide both sides by 2. And then we reduce. 2 divided by 2 is 1. So again, what does x equal in that equation? It's 1. Example B is a little bit more challenging because right now I have a base 2 and a base 32. Well, I can change that 32 to the same base. And how I do that is I understand that 2 to the 5th power is 32. And then the left side just stays as it is. Now we can use our one-to-one property. The bases are both 2, so that means our exponents must equal each other. So 2x minus 3 equals 5. So we solve it using our inverse operations. So we would add 3 to both sides. Simplify. 5 plus 3 is 8. And then we would undo that 2, so we divide both sides by 2. And we get x equals 4. All right, example 4, solve for x. Again, we want to use our special properties. So here's our special properties here. All right. So what we have in example A is a logarithm. And what we can do sometimes to help us is to change it to the other form. So we're going to change it to an exponential equation. So my base is 5, my exponent is x, and then what it equals is 125. And now what we want to do is find out what x equals. So I'm going to go ahead and change that 125 to have the same base. So 5 to the third power, 5 times 5 times 5 is 125. Now I can use my 1-to-1 property. My bases are both 5, so my exponents equal each other. All right, here's another example. We have a logarithm. We're going to change it to an exponential. So my base is 5, my exponent is x, equals 1/5. And right now the bases are not the same, but I can change it to be the same. So I'm going to put a little 1 there. There is a rule that says when you have a negative exponent, like that, you can flip it down below. And that's what we're going to do here. That's the negative exponent rule. So this right side, if I flip it back up, that's going to be a -1 power. Now my bases are the same. My bases are the same, so my exponents have to be the same, so they're equal. So x equals -1. All right, here's a couple of examples with the common log. So notice that this logarithm does not have a base, so it's understood that that's a base 10. So if you get confused, just always write the number 10 in. Like that. So there's our logarithm with base 10, and now we're going to change it to an exponential. So our base is 10, our exponent is x, equals 10,000. Now I want to change this right side to the same base. So 10 to the fourth power is 10,000. And then I have 10 to the x on the left. Now I can use my 1-to-1 property. My bases are the same, so my exponents must equal. So x equals 4 in that equation. All right, here's another common log problem where we do not have the base written down. It's understood that that's base 10. So I'm just going to go ahead and put the 10 in. Now I'm going to change it to an exponential. So it's 10 raised to the x equals 0.01. Now this one's a little harder to do. 0.01 is equivalent to 10 to the -2 power. Now our bases are the same, so our exponents equal -2. Feel free to try the check for understanding before you come to class tomorrow.